China has taken a major step forward in military aviation with the successful testing of its first variable cycle engine, also known as an adaptive cycle engine. This new engine technology is designed to make future fighter jets, possibly including sixth-generation aircraft, more powerful, efficient, and versatile. What makes this engine special is its ability to automatically adjust airflow for different flight conditions, giving aircraft both high speed and fuel efficiency without sacrificing performance. The project was developed by the Chinese Academy of Sciences Technical Institute of Physics and Chemistry, and it features what engineers describe as a triple bypass design. Unlike traditional engines that have a fixed airflow pattern, this advanced engine can channel air through 3 different streams depending on the situation. When a jet needs extreme power for combat or takeoff, the engine boosts thrust. When it is cruising or loitering, the engine automatically shifts to a fuel-saving mode. This design allows for smooth transitions between speed and efficiency modes, addressing what has long been a challenge in aircraft design, balancing power and fuel economy while keeping the engine cool under high temperatures. During testing, the Chinese team completed both ground trials and high-altitude simulations to push the engine's limits. In ground tests, they measured how well the engine performed under controlled conditions, while high-altitude trials simulated flight conditions at speeds up to Mach 4 and altitudes of more than 20,000 meters. These tests showed that the engine could switch modes in less than half a second, maintaining stability through the process. This rapid adaptability is a critical requirement for modern fighter jets that must operate seamlessly across subsonic, supersonic, and even hypersonic speeds. The reported performance gains are impressive. The specific thrust, which measures the engine's power output relative to weight, rose by nearly 28%. Thrust per unit area, a measure of how efficiently the engine produces force for its size, increased by 33%. At simulated high altitudes, the engine's thrust improved by 47%, while fuel consumption decreased by almost 38% compared to current engines like China's WS-15, which powers the J-20 stealth fighter. Overall, the new design could boost fuel efficiency by 25 to 30%, giving future aircraft longer range and endurance. Such leaps in performance come from using advanced materials, including ceramic matrix composites that can handle extreme heat and lightweight single-crystal turbine blades that sustain higher pressures. The engine also uses a fully digital control system, which automatically adjusts performance parameters for maximum efficiency. The variable bypass ratio, ranging from about 0.3 during intense combat to around 10 during cruising, means the engine can transform its internal airflow to suit different missions. It can deliver raw power when needed and then shift into a quieter, cooler, and more economical mode during long flights. Beyond just better speed and range, this engine could enable new kinds of aircraft capabilities. The advanced cooling and energy management systems would make it possible to power directed energy weapons, next-generation sensors, and onboard artificial intelligence systems without overheating. The improved thermal management, estimated to be 2 to 3 times greater than existing engines, could also allow jets to stay stealthy by better controlling heat emissions. While there are still hurdles to overcome, such as perfecting flight reliability and aerodynamic integration, this milestone shows China's growing strength in jet propulsion. It reflects a move toward full independence from foreign engine technology, narrowing the gap with U.S. systems like General Electric's XA-100 program, if successfully integrated into future jets. This adaptive cycle engine could redefine what Chinese fighters are capable of, marking a significant shift in global air power dynamics.